All right, so a little note there. So we're going to do 2 days of solving equations. Today we're solving exponential equations, which just means they're given in exponential form. And tomorrow we're doing solving logarithmic equations. But really, like, it's a mixture of both. We're going to end up, so like this little note says, sometimes we can solve exponential equations by equating the bases of both sides, right? So if, like we just saw in that learning goal, if you can express both sides with the same of an equation with the same base, then do that. Okay. The third bullet there says, if you can, do it. It's good. It's good practice. It might be faster to use logs, and you know, if the instructions didn't say that you had to, then you can do whatever you want. That's fine. But honestly, for now, it's really good practice to think about this stuff this way. So if you can, I would say do it. That's what we're going to do today. But you can always take the log of both sides. I think we're going to see a little bit that taking the log of both sides or rewriting in logarithmic form, they're like the same thing. So you could really, I think in all cases, look at it either way. So that's up to you. Okay. But we'll take a look at what both of those mean. Any questions? All right, let's get started. Solve each of the following. So for this one, I notice that I can express the base of both sides. Like the right side of the equation doesn't necessarily look like a base, I guess, in some ways, but it is. So I can express both sides as powers of 2. So let's do that. So that's 2 to the 4, all to the x minus 2. And you might do the right side in a couple of steps. I'll do it in a couple of steps. How about that? So that's like 8 to the negative 1/2. So that brings the 8 back up and takes care of the square root. And so then 2 to the 4, all to the x minus 2. I multiply those, so that ends up being 2 to the 4x minus 8, distributing the 4 through, equals 2 cubed, all to the negative 1/2. So that wouldn't have been too hard to do in one step, but especially for a lesson, it's nice to see it kind of the long way. Okay, so I've got them expressed in the same base, so therefore the exponent of one must equal the exponent of the other. And I'm multiplying, so I'm doing a little bit of work there. And I'm going to run out of room here, but 4x equals 3/2 plus 8. So 3/2 plus 16, or sorry, negative 3/2 plus 16/2 should be 13/2, and then divide by 4. I think that's 13 over 8. Okay, the next one, I got a base of 4 and a base of 17. Can't be expressed the same way, so you have to use logs. So I can like just rewrite this. It's in exponential form. I can rewrite it in logarithmic form, which would look like this. X equals, the base stays the same. So x equals log of 17 over log of 4. Didn't say how many decimal places around to, but we'll do 2. I know that's an easy question. We've done that a bunch of times. Just to remind us what it's like to rewrite it in log form. Everybody good? for C, we could also rewrite this in log form. We're going to do something, we're going to do it a little bit differently. We're going to take the log of both sides. Okay, just like multiplying both sides by 2 or dividing both sides by 10. It's the same thing. Take the log of both sides. And so what would that look like? It would be log base 10. Don't forget, we don't write it, but it's there. Equals the log of 2. Well, from yesterday, what can I do with the left side? I could take the exponent, write it out front. So 3x times the log of 1.3 equals the log of 2. Divide both sides, and then I'm just going to start isolating for x. So here's where, like, we don't start evaluating things and use decimals. We got to be able to do it all together. So divide both sides by log of 1.3. I get 3x equals log 2 over log of 1.3. And here's where if you, well, maybe I'll do it in a minute, but if we rewrote in logarithmic form, like we did example B, once we get to this step, it would look the same. Okay, so either way, it is the same thing. And then divide both sides by 3, so x equals, you might like doing it like this. Sometimes it gets a bit messy. We actually put the divided by 3 out there. Or, as long as you get this, oh, I kind of ran out of room here. I can include it with the bottom, right? But you got to make sure you know how to enter that in your calculator. So, you know, if you put it out here, whoops, I can just do log 2 divided by log of 1.3 equals, and then at the end divide by 3. And I got 0.88. Try that. Make sure you can get that answer. And in the blue, you can see that's what it would look like if I rewrote both sides. My exponent equals log base 1.3 of 2. And so 3x equals log of 2 over log, 1.3. And then divide both sides by 3 and continue. So you really need to understand both. I know it's kind of the same thing, but taking the log of both sides, like, that's something that we do. That's something you need to understand. So don't just always think of it as rewriting. Okay. Any questions? Everybody get that okay on the calculator?
There's a blue VW MPV in the back parking lot, license plate EFTW662. Your lights are on.
Okay, so just like equations from grade 9, we got to kind of move things around and isolate for x. So you never know what you're going to get. So we're just going to subtract 25 from both sides. Take the log of both sides, and when I do that, this is going to be the log of 75. I can take the exponent out in the same step. That's like a standard way of how we would write this. Okay, and then from there, just divide both sides. So log 75 over log 2 equals x plus 3. And so x equals log 75 over log 2 minus 3. Try that one on your calculator. Pretty easy, pretty straightforward though. I think. Whoops, what's going on? I think my calculator's on its last legs here. I got 3.23. Again, when I did log 75 divided by log of 2, I got like 6.2. Does that make sense? 2, because this is one that we could understand, right? Log of 2, that means like my base was 2, right? So 2 to what exponent would give me 75? So 2 to the 6 is 64, 2 to the 7 is 128, so somewhere between those. So that kind of makes sense if you're thinking it through. And then we just see all different kinds of combinations. We're going to do some applications today. And when you do applications, you end up getting, junky things like this with a bunch of stuff in the exponent and sometimes, just different numbers all over the place. So every question might be a bit different. In this case, divide both sides by 10. Take the log of both sides. Hey, you can go ahead and try to finish that one. All right, so should have got, what happened? Should have got 10.84. And let's just see if we can take a little look at this. Yeah, so much glare. Ugh. I don't know what to do. Okay, it'll be fine. So here's what I did. I got 4 log 3 divided by log 1.5. That was my answer, 10.84. And then I thought, well, I just want to make sure that that's right. So I'm going to go 10, if you're good with your calculator, which I'm sure most of you are, times 1.5 to the bracket, because I got to get the exponent in brackets, right? this is like a left side, right side check. To the x, the answer key on your calculator. If you've never used it, oh my gosh, you're missing out. It's one of the best resources on there because it just holds that last answer, right? You can put it in wherever you want. Divided by 4. So if I know it's really hard to see, but get your answer divided by 4. There we go. That's a bit better. Equals processing 30 exactly. Nice little check on a test that you're on the right track. Everybody good? All right. Got a few more examples here. These ones are a little bit different. Very different, I should say. Though we've seen almost everything like that already. So that was a little bit of just, reminder and more practice. We've seen those kinds of questions before. But it's funny how we've seen them. You saw those last year, I'm sure. And you've seen that we've already done that kind of stuff this year. But then all of a sudden we do an application and people are like, I don't know how to do this. right? But it's the same thing, and we're going to take a look at an example later, so just keep that in mind. But here's some of the new stuff today, F and G. And I think this would be the kind that if you never saw one of these, it'd be hard to figure out what to do. But once you've seen it, and once you've done it a couple of times, they're basically all the same. And if you practice a few times and it clicks, it becomes easy. Okay, so the trick is there's a common factor here. I'm going to rewrite this like this. 3 to the x times 3 to the 1. Do you agree that this part is there? Those are the same? Do you see that? Add the exponents, multiplying powers of the same base. 3 to something times 3 to something, something plus something, right? So x plus 1. Everybody good with that? And just for kicks, I'm going to write this the same way. So this is 3 to the x just times 1. Now I have a common factor. So these questions are specially designed to work. They don't have to work out exactly, although often they do. You could end up by taking the log of both sides. But often, for whatever reason, they work out. They're designed to work. But it's the common factor. Like, there's not another way to do this. You got to know that when you see, first of all, they have the same base. They're both base 3. Right? So, okay, that's a tip. But when you have like exponents in different places, we can't isolate to take the log of both sides. The only way that this is going to work is by common factoring that out, which again only will work if they have the same base, and then I can do it. So what is 3 to the 1 plus 1? It's 4. So 3 to the x equals 972 over 4. 3 to the x equals 243. Look at that. Right? So that means x equals log base 3 of 243. And I know I said earlier that, it's funny. I said earlier, if you can do it by expressing them in the same base, do that. And now I'm not. But also I want you to know, like I think we talked about this yesterday, but it is okay to do it this way too, and then just write the answer. Or I could have done it 3 to the x equals 3 to the 5. I guess both of these are like kind of solving by inspection. Like I know that 3 to the 5 is 2/4, or I try a few different. I know it is a power of 3, so I try a few to figure out which one it is, and then just write the answer down. Right? This is just also like now we can start just writing it that way. We used to sort of try to show our work or show our thinking, but we can just go straight to that answer. Okay, so why don't you try the first step of this one? You don't have to, the first step that we did here, if you like to write it that way, that's fine. Like if it helps with your thinking, especially early on, great. But normally, that's not like a normal part of the process. We usually sort of jump to this step once you see it. So if you want to try that, you can do that. Okay, so hopefully you got something like this. 2 to the x is going to be my common factor. Like you'll get used to that, right? It's going to make this part here 1. And I get 2 cubed minus 1 So 2 to the x equals 112 divided by 7. 2 to the 3 is 8, minus 1 is 7, so divide both sides by 7. 2 to the x is, look at that, 16. Therefore, x equals 4. All good? Questions? One more type. I think this is the last type. Then we're going to look at an application or two. So I just finished saying you can't do it if you have logs of the same bit or different bases or exponents of different bases. The other type that had like 2 on one side equals a number, that's one type. This we can do because there's a single exponent on both sides. We've already seen this. There's an x in both of the exponents, but that's okay. We can do that as long as we have like single exponents like this. Of course, anything else is possible. It's just, possible with our skill set. So what we're going to do is we're going to take the log of both sides. Start with that. So again, this is why it's something that you kind of need to know how to do, not just rewriting it in exponential form. So this is going to be log, and I'll do this the long way, but you could skip this part in the future. Log 10 to the x minus 2. So I can bring the exponent down, and I get, x plus 1 times log of 4 equals x minus 2, brackets, times the log of 10. I'm going to expand. So x log 4 plus 1 times log 4, which is log 4, equals x log 10 minus 2 log 10. Move the x's to one side and the logs to the other. Okay, so I'm going to try to keep things positive. So I'm going to move the x's to the right. So I get log 4 plus 2 log 10 equals x times log 10, minus x log 4. Does anybody see where this is going? Or does this seem strange and a little scary? So now I can common factor the x out of the right side. And divide both sides by log 10 minus log 4. So again, these questions the math tends to be very repetitive. Like you end up, taking the log of both sides, expanding, moving the x's to one side, common factoring, then dividing by that big chunk thing. And you get very similar answers. So if you've tried it a few times, it is a lot of steps. Okay, but they're repetitive steps. And then putting it on your calculator is going to be a bit tricky. So just as long as you put everything in brackets on the top and on the bottom, it shouldn't be too bad. Bracket log 4 plus 2 log 10, bracket divided by bracket, log 10 minus log 4. Try it if you like. I got 6.54. Any questions? Somebody asked me recently, do we do financial math in this class? Like, we don't do any. There are applications that are financial, but there's no like unit on financial math like that. That's part of the grade 11 course. So these questions are exponential questions or log questions. So we see them in applications, but we're not doing anything more with them. Like we saw the exponential decay question the other day. Those are common ones, or other kinds of growth questions, or once in a while these interest questions as well. But we're not like spending a day talking about financial math or anything. So if you remember from grade 11, there's a formula that you need in order to solve these. And it goes something like this. A equals P times 1 plus I to the N. I think this is written out in the textbook, so I'm not going to write it all out, but P is the principal. That's the amount you start with, the amount of money you start with in your bank account or in your investment. A stands for amount, so that's the final amount. That's how much you have after it's gained interest. I is the interest rate per compounding period. We'll talk about that in example 3. For this one, it's just the interest rate. And N is the number of compounds. It's kind of the number of years, but it's also kind of the number of compounds. So we're going to look at that in a couple of different ways. So because this one's just just compounded annually, it's just the number of years. Okay, so A equals P equals, it's a good idea to kind of write all this stuff down. I is 7.5%, so 0.075. And N is the thing I'm asked to solve for. Now this is interesting. It doesn't give us a P and it doesn't give us an A. It just says, how long will it take for investment to double? So this is something I want you to think about. There's a few questions in the practice like this, but they give you amounts. But I like this thinking where, like, if I put in $1 and it doubles to $2, I've only gained $1. If I put in $10,000 and it doubles to $20,000, I've gained $10,000. Those would happen in this situation in the same time period, right? Because the interest is relative to how much money you put in. So you would earn $1, and the same time you would earn $10,000, depending on how much you put in. Like, that's how exponential growth works. It doesn't matter what your input is and what your output is. It's the relativeness between the two that matters. So I can say A is 2 and P is 1 to make the math easy. So I get 2 equals 1 plus, 0.075 to the N. Because imagine I had $20,000. Like, what am I going to do in my first step? I'm going to divide both sides by 1. Doesn't do anything, right? But imagine I had 20,000 here and 10,000 here. I divide by 10,000. I just get 2 over here anyway. Right? Doesn't matter. You see it in the first step of solving. The input doesn't matter. And that's maybe a little bit of a strange thing. If you look at exponential growth and compound interest, you look at these situations, it makes perfect sense. But that's one of those things that's surprising to people about maths, that you would get $1 and the same time you'd get $10,000 depending on what you put in. Vivian.
Can we just sub in like x and 2x for please?
You could even do that. That would be awesome. Yeah. Yeah. Although then you'd be dividing by x and you have to be like, where it doesn't equal 0, but which it wouldn't in this case anyway, but yeah. I think the textbook gives you numbers. I've done these questions in lots of courses where I don't, and I would want you to I would say just pick 2, 1,000 and 500. If you did x and 2x, that would be like bonus, but you wouldn't even have to. Reminds me of another surprising thing in maths that people never believe. When you play the lottery, the odd, like if you pick the numbers 1, 2, 3, 4, 5, 6, your odds of winning are just as good as anybody else's. They pick different numbers. People go, "No, that's not true. It's never going to be 1, 2, 3, 4, 5, 6." No, the odds of that are exactly the same as any other combination of 6 numbers. People never believe that. Like, no, those numbers are in a row. That'll never happen. Well, really, that the odds of ever winning the lottery are astronomically against you. It's never going to happen. But anyway, people don't believe that. Okay, so let's solve this. So 2 equals 1.075 to the n. Maybe this one I want to rewrite this way. So n equals log base 1.075 of 2, which is log of 2 over log 1.075. This is like an easy one. Whoa, ran out of space there. Log of 2 divided by log of 1.075. So this gave me 9.58, so 9.6. What does that mean? Therefore, it will take Jessica about 9.6 years. I'm not too worried about how many months that is or how many it is exactly. Like if this was a big deal, you could never round down because it wouldn't have doubled yet. You know what I mean? Like you'd always have to round up. Like there's all these things, but I'm not too worried about that. We're not really spending enough time on it, so I'm sure that's something that you guys could think about, figure out pretty easily. Sometimes in money, like if you take accounting or business class, that's a big deal. When does it actually? Or like if you're making payments on your house, when does the actual last payment you don't just round. Like the bank doesn't just round money away, right? It's like you got to calculate these last few things. But anyway, but mathematically it's all pretty easy. Pretty good with that? One more example. So this one's a little bit different because it says compounded monthly. So while you're writing it down, I'll just comment. It's the 6% is missing something. It's assumed. You'll see in the textbook they're always very good at this. It'll say like /A means per annum or per year. I think that's Latin probably, and it's just stuck around. So interest rates are always given yearly. Okay? That way you can compare one interest rate to another always with the same sort of like kind of like comparing fractions with the same denominator, right? They have the same units essentially. But if it's compounded monthly, it's not 6% every month. You take the 6, divide by 12. That gives you like 0.5%. So you're actually getting 0.5% every month. That's how it works. Which is more interest than 6% per year. Compounded more frequently is a better investment, gives you more money. Again, if you took like a financial math course, that would be like day one. Hey, compounding more frequently is better. Okay. Reminds me of a different video I just watched recently. So anyway, but that's what that means. So when it says compounded monthly, we have to do something important, but we're still using the same. So, but what I'm going to do just for these questions is I'm going to call it n times c. So there's sort of two ways that you could go about doing this. You could leave it as n, and you'd get the number of compounds. You'd have to understand what you have. I'll talk about this when we get to the end. It'll make more sense. Understand what you have, and then you're going to like make sense of your answer. Or if you just remember to add this times c, where c is the compounds per year, then the math will kind of work itself out. Okay, so how long will it take the investment to grow to $10,000? So A is 10,000. You have to be able to identify the givens, obviously. I hope that this is familiar and that this isn't the hard part. I, careful of this, take the 6%, convert it to a decimal. Divide by 100 if you have to on your calculator, but you should be able to do that in your head. And divide by the number of compounds per year, right? So compounds per year, like C. That's what that 12 was. And we can say C equals 12 and N is question mark. That's what we're looking for. Is that good for everybody? Ooh. Yeah? Everybody okay? So if it was quarterly, that's 4 times a year. It's 4. I don't think there's anything else in the textbook, but like there's all kinds of different ones. Semi-annually, semi-monthly, bi-monthly, bi-weekly, weekly, daily, 365, right? Like there's all different kinds. But I'll let you think about that, figure that out, ask if you're not sure. All right, let's plug our numbers in. 10,000 equals 3,000. 1 plus. So 0.06 divided by 12 works out. So I'm going to use that. But once in a while, it doesn't. And you would just have to leave the fraction in there. It gets a bit messier, but I think there's one example works that way. So there you go, 12n. Divide both sides by 3,000. And I'm just going to use this fraction, 10 over 3 equals 1.005 to the 12n. Take the log of both sides. So 12n log 1.005. Is everybody cool with that? Divide by log 1.005. Equals 12n. And so divide by 12. So just watch for a minute. You can copy the rest of this down later if you need it. But so what I'm going to do is I'm going to do log of 10 over 3 divided by log of 1.005 equals, that's going to give me some big numbers. So 241. So that's like, in this case, that'd be 241 months. It's a number, like that's how long it would take. Because I haven't divided by 12 yet. So this is the thinking that you should probably do some of this thinking when you're doing these questions for the textbook. So it sort of makes sense of it. If you know that formula, like the formula I gave you, here's the thing. The formula I gave you is not a real formula. N times C is not a real thing. It works fine, like it could be a real formula, but it's not really a standard formula. Like I think the textbook, whatever, expects you to do this, understand that's months, and then if it's supposed to be answered in years, divide it by 12. But if we add that little times C, then the math takes care of that. But it depends. What if I gave you a question on a test, or what if there was a question in the textbook that said, how many months? And if you added the times C and you divided by 12 here, that'd be the wrong answer. Because that formula is designed to calculate the number of years. So that is a bit of a tricky thing about financial math, is like what's it trying to get you to answer? But then when I divide by 12, the textbook questions are all answered in, I think they're maybe even in both, but I think they have answers in years. And maybe some of them are in months too. So there you go. So 20.1 years. That's a long time. Sure, it's free money. It's $7,000, but 20 years? Oh my gosh. Therefore, it will take 20.1 years. Any questions?